Hi, this is going to be a basic overview of strong and weak acids and strong and weak bases. It comes with a lot of good information in this and easy ways to tell them apart. First off, acids. So a couple of things that you guys probably have already picked up is the two basic definitions that make up an acid. The fact that acids will donate a hydrogen ion or they will produce a hydrogen ion in solution. And here's a couple of examples. You have hydrochloric acid, and this is actually citric acid. That's the acid that you find in oranges and lemons that make them sour. One of the things you probably notice is that the hydrogen, the one that's ionizable, is always written in the front. And we say it's ionizable because that is a hydrogen that will pop off of the rest of the acid, and that's the one that gets donated in solution. Bases are going to be your substances that produce the hydroxide ions in solutions, and also by definition, they are the ones that accept hydrogen ions when reacted with an acid. The formula is a little bit harder to tell because there's a difference between strong and weak bases. The strong ones are going to be easy. You're going to look for the hydroxide ion in the formula, but the weak bases don't. So how do we find those? And I'm going to go through some things that you can look for to figure out which one's an acid or a base. So here's just an example of sodium hydroxide. It's a very classic strong base. You can see the sodium, which is the Na+, has dissociated from the hydroxide ion. All right, so your strong acids, there are only 7 of them, and they're all listed here. There's the name of the acid, there's the formula of the acid. Now, do you have to memorize them? No, you're not required, but you do have to know what they are. So I just kind of keep a list on the side. Don't worry about this Ka. Okay, and so essentially, if it's not one of these 7 strong acids, it will always be a weak acid. So if it's not one of these 7, it will be classified as a weak acid. And that will come in handy when you start to write dissociation equations for them. So here's an example of a strong acid dissociation equation. One of the things you need to know, it is always complete dissociation. So that means every single acid molecule that gets dissolved will break apart into hydrogen ion and the rest of the ion, the anion. So it could be a single anion like chloride or fluoride, or it could break into a polyatomic ion like nitride or nitrate. So one of the other things you would know for complete dissociation is when we write the equation, it is always a one-way arrow. It's not reversible. That one-way arrow is a giant clue that it's a complete dissociation. You always have the full acid molecule on one side and then the 2 ions it breaks apart into on the product side. So those are for your strong acids. Your weak acids behave a little bit differently in solution. So notice I've written that it's incomplete dissociation. Most of the molecules actually do not dissociate. So what you can see here is you can see all of these weak acid molecules. Once they're in solution, most of them stay intact as the entire molecule. Only some of them dissociate into the hydrogen ion and that negative anion. So when we write the equation, you'll notice it's now a two-sided arrow. This is how I do two-sided arrow in PowerPoints. So that two-sided arrow tells you that in solution, you're going to have the whole molecule, that's all of these guys. You're going to have some of the hydrogen ion right there, and you're going to have some of the negative anion right there. Okay, so that's the biggest difference between weak and strong acids, how much they dissociate and how they're written in an equation. Strong bases, on the other side, on the other hand, it's more straightforward when we talk about strong bases. They're going to be metal hydroxides, and it's not every single one. It's these. These metal hydroxides are the only ones that will be a strong base. If it's not one of these, it's not a strong base. Okay? And so when they dissociate, it's also complete dissociation. All your ions will break apart. So you really have to pull in that knowledge about ionic compounds and dissociation. So here's an example of calcium hydroxide. It's a strong base. It dissociates into one calcium ion and 2 separate hydroxide ions. Another example is sodium hydroxide. It's another classic strong base we use a lot. Sodium hydroxide breaks apart into sodium ions and then individual hydroxide ions. When we write them in equation, notice it's also a one-way arrow because it's complete dissociation. On the other hand, your weak bases, these are your tricky ones. because they don't have that OH, that's a telltale sign you've got a base. You can only figure out if they're a base by looking at what they do. And so you want to look for the fact that they're taking a hydrogen away from an acid. You have some sample weak bases, some of your polyatomic ions. So I listed some here. Those can act as a weak base because they have a negative charge that can steal hydrogens. Some molecules, such as SO2, that's right there, it's got lone pairs, those electrons, that can take the hydrogen away. Or NOx. NOx just means it could be nitrogen dioxide, nitrogen trioxide. Those are also weak bases. NH3 is the ultimate weak base because it's just used a lot in a lot of examples. And you can see that lone pair right there on the end that can take the hydrogen. And how you would see these weak bases in solution, you would see that double arrow show up again. The key difference with weak bases and all the other acids and bases is that weak bases do not dissociate. They don't break apart. Your strong acids dissociate. Your weak acids dissociate. Your strong bases dissociate. Your weak bases do not dissociate. What they do is they take hydrogens from the acid, okay? And some of them take hydrogens from the acid, which makes it weak. Some of them take the hydrogen. So here's an example of ammonia. You can see that there's 3 hydrogens, 3 little white spheres. Once in solution, the ammonia, most of them stay intact. They don't, actually they don't react, sorry. So most of the ammonia is still NH3 in solution. Some of them have now claimed an extra hydrogen. They've stolen it from water, okay? Here's another example. Here's a phosphate ion reacting with water. It will take one of the hydrogens, and I just realized I did not finish that equation. Yowza. So let me change that real quick. Okay, there you go. There's the other one. So that phosphate took one hydrogen away from the water to become HPO4 2-, and that's how you would know that it is a weak base. One, it's a phosphate. Also, two, you want to look for those reversible arrows that indicate it's a weak base. So that is it. That is strong acids, strong bases, weak acids, weak bases. How you would tell that it's a stronger weak acid or a stronger weak base by looking at them in the equation and how they behave. If you have any questions, you can always email me. Thank you. Bye-bye.